Thanks for your introduction. I also would like to thank to the organizer to give me the chance to stay here for the whole program. I really enjoyed this visiting experience. Today I'm going to present the main project I've been done during my postdoc period. This work is collaborated with my advisor Chang Du and his 2 PhD students. And Xiao Chuantian is also sitting, no? Oh, sitting over there. Okay, so this can be seen as a parallel talk to her talk on Monday. In her talk, she focused on the asymptotic compatible analysis on the finite element. So today I will present another 2 discretization, the finite difference scheme and the Fourier spectral method. Okay, here's the outline. First, I will give you a short introduction on the motivations. In the second part, I will present 2 asymptotic compatible discretizations. Then we will apply the Fourier spectral method to simulate some nonlocal gradient flows. And in the end, I will give you several remarks on the summary and future work. Okay, thanks to the earlier talkers, I don't have to speak too much on the background introduction. The mathematical model we are going to investigate involving modeling fractures. So it's one very important topic in material science engineering. Of course, there are many different approaches towards modeling fractures. Basically, we can classify them into 3 classes. The first one is classic theory of fracture mechanics. It uses the partial differential equation to capture the continuum media and use actual equation to capture the evolution of cracks. So it's limited by the multiple propagating cracks. The second class is atomistic modeling. Is the bottom-up approach is from atomic scale to macroscopic scale, and is usually limited by the size of real sample. Recent years, there are some non-local modeling. One of them is this paradynamics model is proposed by Selin in year 2000. So in the paradynamic model, and the differential equation will be replaced by integration equation, so it allows solution to be more singular. It can describe the cracks. And on the other hand, it can be reduced to the classical PDEs in certain cases, so it can describe the continuum medium. So based on these 2 features, it can handle the continuum medium and cracks within a single framework. So, okay, let's look at the paradynamics. So basically, we can view it as Newton's second law. U here is the displacement, so U dot prime is the acceleration, and the total force will be contributed by 2 parts. This red integration part is the non-local interaction with its neighborhood, and B is the loading force. Okay, so the core of the model is try to identify the force density function F. If we denote eta as the relative displacement and Kc as the relative position in the reference configuration, then eta plus Kc is the relative position in the deformed configuration. Of course, this density function should satisfy several restrictions such as linear and angular momentum, and we hope it require less spatial regularity. In this paper, the author pointed out the Hooke's law satisfies these restrictions. So from Hooke's law, we know force is proportional to the relative change given as this form. We can say this density function can be nonlinear in terms of eta. So next, we try to linearize this density function. If we assume small displacement, so eta is small, and with isotropic boundary spring system, then this function can be approximated by this linear term in terms of eta. So delta is the horizon parameter. It represents the range of non-local interaction. And if we plug in this linear approximation into the model, we get this linearized PDO model at this one. If we take the red integration denoted as the linearized PD operator, so in this talk, we only focus on the scalar case, given this one. And so far, there are many mathematical analyses have been done on this linearized PD operator. one of the notable work is done by Du, Gansberg, LaHogue, Zhou in year 2012. And in this paper, they studied the volume constraint problem. Here, omega delta is the boundary layer. Okay, it's not just the boundary curve, it's boundary layer, given this one. And they study the connections between nonlocal equation with fractional PDE and local PDE. And we can view the fractional PDE as a special case of the nonlocal equation if we take the horizon parameter goes to infinity, take the fractional kernel here. And on the other hand, as delta approaches to 0, then the nonlocal interaction vanish. The model is reduced to the local linear diffusion equation, at least one. In this case, we also call this operator as nonlocal diffusion operator. And so in this work, we are particularly interested to design numerical scheme to preserve this local limiting behavior. So we call such schemes as asymptotic compatible schemes. This concept is first brought up in this paper by Du and Tian. And the AC scheme not only required convergence, but also requires this AC convergence. The AC convergence is the numerical solution of nonlocal model converge to the exact solution of local model as the horizon parameter and the mesh size go to 0 simultaneously. Usually, it's difficult to show this AC convergence directly. We can use some triangular inequality to split it into different convergent parties, shown as in this diagram. I will use these convergent parts in the later section. Okay, I don't. And first, I want to claim the AC discretization are not granted. So let's see some examples. First, for this naive quadrature discretization, we just given this form. Here's a summary of this discretization. And the good side is very simple and convergent for if we fix delta just for integral kernel, okay? And however, the error is given in this form. And here there is a fractional factor here. So for small delta, it requires the mesh size should be very, very small. And is of course because of this factor is not consistent with the local limit. So as delta go to 0, if we choose fix delta equal to 3h, we let delta and h go to 0 simultaneously, we have these simulations. So we can see the numerical solutions don't converge to the local exact solution of local model. So it means this naive quadrature is not asymptotic compatible. And for singular kernels, we have some other issues. And this is another frequently used scheme, the collocation discretization. So if we try to approximate the solution by piecewise constant or piecewise linear function, we plug in this approximation into the operator, we get this collocation scheme. So it's not easy to compute the error. Actually, we have the uniform inverse boundedness. So this truncation error is, at least for small delta, is the global error. Okay. Since we have the second moment is uniform bound at some constant c. So for small delta, this red integration is asymptotically equivalent to this term. So it is a non-fractional factor in terms of delta here. So we have the similar summary for this collocation discretizations. So it also simple and convergent for fixed delta works for integrable kernels. And because the error is in this term, so small delta will deteriorate convergence rates. Okay, so it's also not consistent with delta go to 0. It will fix the ratio between delta and h. It still have trouble to handle the singular kernels. So we have several reasons why these AC schemes are necessary. So the first intention is try to remove this delta fractional factor here, okay? Or at least make the alpha greater than beta. Because in this sense, when delta is very small, it doesn't need to require h be very small. It allows the h can be the same scale as delta. And secondly, it's useful for verification and validation. It can guarantee the consistency with the classical solution. And thirdly, there are several talks about the multi-scale coupling modeling. So in this multi-scale modeling, in certain regions, the local model or very small delta are used, or in certain regions, non-local model are used. So the AC scheme can make sure the transition be smooth or moderate. Okay. And in the end, we hope this AC scheme is robust for singular kernels. So this. And so far, there are some work have been done on this AC scheme, such as finite difference have been done by Tian, and some just finite difference for 1D. So, but there's still some limitation of the existing work. So in this talk, we try to complete these limitations. First, there is no AC finite difference scheme for multi-D. There is just for 1D. Okay. And secondly, there is no Fourier spectral implementation. We need to conquer two difficulties to make this implementation accurately and efficiently. We should find out ways to evaluate the non-local eigenvalues, and we should find out ways to handle singular non-local solutions. As we know, the non-local solution can be singular. So if we want to use Fourier spectral method, we need to overcome this. Okay, and there is no such AC property, and that's for nonlinear non-local models. Okay, first part, we try to get the asymptotic combined finite difference scheme for multi-D. So suppose we have a uniform mesh at any grid point. We rewrite this non-local operator by introducing this weight function. Okay, just divide 1 and multiply 1. Then we do the piecewise linear interpolation on the blue part. Then we get this quadrature-based finite difference scheme. So the case stable is to choose the weight function here. Okay, so we hope this weight function can achieve two goals. First, we hope it guarantees the convergence and AC convergence. And it works for multi-D and singular kernels. Fortunately, in this work, we found a perfect weight function given at this form. Okay, there are several benefits for this kernel. First is independent of dimension and independent of kernels. So we have verified it's working for multi-D and singular kernels. Secondly, we have these two uniform optimal truncation error. Here we just assume the solution is smooth, okay? And here I want to emphasize the parameter C delta here. Okay, the C delta is independent of H. As delta go to 0, this C delta only depends on the fourth derivative of the solution. We have similar result for multi-D. So it means there is no such delta fractional factor in the error. Okay, and the second truncation error says this is the operator difference actually. So the C is dependent of H and delta. These two truncation error offers us two consistencies to prove this theorem. Okay, so if we solve non-local equation by AC scheme and the local equation by central finite difference scheme, we have this convergence and AC convergence. We can prove this theorem by following the classical way using stability and consistency. Okay, so in the stability is guaranteed by this lemma. Okay, and for this operator, I forgot to mention in this work we consider the periodic boundary condition. Some results can be extended to the Dirichlet boundary condition. So if we just remove the zero eigenvalue here, the smallest eigenvalue can be bounded by this C delta. It means this inverse is bounded by C delta. We can further estimate as delta less than delta zero, this C delta less than some constant. It doesn't depend on delta anymore. Okay, this is the key point to offer us the uniform stability. Okay, so it's the end of the first part. Okay, second part, we try to implement the Fourier spectral method for non-local model. As I mentioned earlier, we need to conquer two difficulties. We have proposed one hybrid algorithm to evaluate these non-local eigenvalues for these fractional kernels. Actually, it not only works for these fractional, it can work for polynomial kernels or some other mixing kernel. I will show this later. Okay, and the second part, we need to find out ways to handle non-smooth data in this work. Okay, first, we can write down the explicit form of the non-local eigenvalue. We consider the periodic boundary condition. Okay, and however, we claim it's a bad idea if we try to evaluate these integrals by some quadrature schemes. This claim based on 2 points. First, if we consider the error for solving this non-local equation by Fourier spectral methods, the errors are contributed by 2 parts. The first part is the relative error of the approximation of non-local eigenvalue. And the second part is the truncation error. It depends on the regularity of F. Okay, so to match the high accuracy of the spectral methods, we need to make this approximation very accurate. So it will cause this efficiency issue. We can see the kernel we consider can be very singular here. Okay, 2 plus D can be. And it highly oscillatory term. Cosine kz can be highly oscillatory for large K delta. And of course, there are many Fourier symbols need to be evaluated. So we need to find other ways except this quadrature evaluation. Okay, so we have this hybrid algorithm. Here I just take the 3D as an example to show the main idea. Actually, it works for 1D and 2D, of course. And for this non-local eigenvalue, we derive 3 different forms of it. So the first one is the original integration form. Okay, we consider the fractional kernel. We just normalize the integration domain. Okay, given this form, we already see it could be costly and low accurate to evaluate it directly. However, we carefully derive the 2 forms, the serial form. So it can be viewed as a parameter A is given at this form. Okay, given this serial form, and this ODE form in terms of A. For this serial form, it's converged super fast for small a. But for large f, first is analytically convergent, this series. Okay, but however, it's divergent for in programming for large A because of the large of cancellation error. We try many different techniques. We cannot make sure this series convergent in programming. And for the OD form, the only drawback is singular at the origin. So if we use some OD solver, it may affect the accuracy. So the basic idea is combine these two forms. So for small a, we use this series form. Okay, and for large a, we use this OD form. We solve it by such as RK4 at certain a. Okay, so such as we start at A0. So we have A0 is not so small. We can evaluate A0 by this series form. Then we can start this RK4 solver. So the accuracy can be guaranteed. Okay, and here I want to emphasize we only need to do phase of time loop for the RK4 solver. We can get all nonlocal eigenvalues simultaneously. So, okay, I omitted this part, the details, okay? And here's one simple example. We try to evaluate these Fourier symbols. We use 3 different methods, the truncated series expansion, and just the centered Riemann sum quadrature, and our hybrid algorithm, okay? So for small a, we can see the truncated series form shown as the red dotted line. It converges super fast. However, it divergent for large A. And in both two cases, the quadrature always consumes the most computation time, okay, with low accuracy. Our hybrid algorithm works well for both two cases. Okay, so it shows our hybrid algorithm can be accurately and efficiently. And second part first, the handling non-smooth data F. As I showed just now, the second term in the error, it depends on the regularity of F. If F is not so smooth enough, the accuracy can be very low. So we propose this splitting technique only for integer kernels. Okay, for fraction kernels, we cannot use this technique. So for integer kernels, first we can separate the operator by 2 parts. This one part and this one part. So the first part is truncated convolution. Okay, so if we split U into 2 parts, then we just plug in this into this equation. We get this equation. If we let C delta V equal to F, we cancel the 2 red terms. We end up with a new nonlocal equation with a new right-hand side. So the new right-hand side is smoother than F. So if we solve this equation, we can improve the accuracy here. Okay. So you will keep repeating these steps. We can get smoother and smoother right-hand side. Actually, we can keep in this splitting technique infinite times. This which will give us the Green's function. This is only the, yes, maybe you wonder, if you have the Green's function, why do you use these numerical schemes? But this Green's function can be a series in terms of very many, in terms of convolution. So it nth convolution with the right side. So it's not efficient to evaluate the Green function directly. Okay. So let's see a very simple 1D example. We try to solve this nonlocal diffusion equation. We choose the constant kernel here. Okay. So K here is the characteristic function. And we choose the discontinuous right-hand side. We can see there is discontinuity located at x equal to pi. So if we just take the regular Fourier spectral method to solve it, we can see there appears some Gibbs oscillation. This is because we try to approximate discontinuous solution by Fourier series, so it's no surprise here. However, if we just do one-time splitting technique, we can kill this oscillation totally. Okay, so this is the end of the second part. Okay, in the third part, we try to consider some nonlinear, nonlocal models. So we start with these two classical free energy as the Ginsburg-Landau energy and the Swift-Hohenberg free energy given in this form. Okay. Both two free energy are obtained by experiments data, I guess. Okay. And later on, they were both reinterpreted by this density function theorem. So essentially, this DFT model is nonlocal here. So this reminds us to use the nonlocal diffusion operator, just replace this local diffusion Laplace operator. Okay, we get this nonlocal analogous for energy. Actually, we can derive this nonlocal energy, assume several assumptions on this kernel and approximation this log function. Okay, we can derive this nonlocal for energy. Then if we take the variation derivative of this nonlocal free energy and follow different energy dissipation laws, we can get these nonlinear nonlocal gradient flows as the nonlocal Allen-Cahn equation, and nonlocal Cahn-Hilliard equation, and nonlocal phase-fit crystal model. Okay, so next we try to use the Fourier spectral method to solve it. So the first result, we try to establish the compatibility for the Fourier approximation for nonlinear models. In this work, we start with considering this linear model. For this linear model, if we solve both of them by Fourier spectral methods, we have this uniform estimate. Okay, there are two significances of this uniform estimate. So first, we can extend this estimate to the nonlinear models. We just need extra stability analysis. Okay, and this is one crucial step to get this AC convergence, as we said, as showed in the convergence diagram. So we used the triangular inequality. We split it into two parts. So the first part is the error or difference between two numerical solutions. This part is completed by this lemma. And the second part is just the convergence analysis for the spectral methods of the local model. So it can be finished in the classical way. So combining these two parts, this can give us the AC convergence. Okay, another interesting result I want to present is the discontinuity formation in the nonlocal nonlinear models. Okay, here I just take the Allen-Cahn equation as an example. So if we consider nonlocal Allen-Cahn equation, the steady state satisfies this equation. If we denote C delta as the integration of the kernel, we have this. We can prove this theorem. If this term greater than 1, then the state is continuous. However, if this term is less than 1, then any non-trivial steady state must have a discontinuity at the interface point. Moreover, we can quantify this jump. Okay, we can quantify this jump. And we have several remarks for this theorem. First, we just use some elementary mathematical analysis tool to prove this theorem, such as the inverse function theorem, maximum principle, and the convolution properties. And this result is very contrasted with the local model. So we know the steady state of local Allen-Cahn equation are always smooth, but as the epsilon go to 0, it recovers the sharp interface. And the similar result can be extended to the nonlocal Cahn-Hilliard and nonlocal physical-crystal model. Okay, so next I will present several numerical simulations. Okay, all these numerical simulations we use Fourier spectral methods for the space discretization. Use the ETD RK4, the exponential time differencing scheme to discretize the time. Okay, and the first one is the nonlocal Allen-Cahn equation. We set delta 0 as the critical point to determine the continuity of the steady state. In the local model, we can see the interface here is very smooth. And for small delta, the interface is continuous at least. However, for large delta, the interface here can be very sharp. And meanwhile, we observe this oscillation here. These oscillations are not supposed to appear here. Okay, but however, it's not surprised because it further indicates that these are indeed discontinuous, because we try to use the regular Fourier spectral method to approximate these solutions. Okay. And the second one is the two-dimensional nonlocal Cahn-Hilliard equation. We did 3 groups of experiments. The first column is the local model for comparison, and the middle part is small delta. We can see the solutions are very close to the local model. This, in some degree, it shows the AC convergence of Fourier spectral method. However, for the large delta, the solution can become more heterogeneous here, and the interface here is much thinner comparing to the local model. Okay. And the last example is two-dimensional nonlocal physical-crystal model. As I mentioned, we not only consider one single fractional kernels, we consider this mixing kernel in this example. Okay. It turns out the nonlocal eigenvalue of this mixing kernel is just a linear combination of these two nonlocal eigenvalues. Both of them can be evaluated by our hybrid algorithm. So we can evaluate this mixing nonlocal eigenvalue by this hybrid algorithm. In these experiments, we increase the C1 parameter, okay? Then we observe the size of the cell become larger and larger. The energy evolution and the residual evolution indicates our simulation almost reached the steady state. Okay, summary. In this work, we proposed two asymptotic discretization for the nonlocal equation for the quadrature-based finite difference. We extended from 1D to multi-D. And we proposed two techniques to make the implementation of Fourier spectral methods accurately and efficiently. For the nonlinear nonlogarithm flows, we first establish the AC convergence, and then we show this discontinuous formation both analytically and numerically. Okay. For the future work, first we would like to do some ongoing work, such as the nonlocal model in space model with directionally boundary condition. As I mentioned, the solution behavior can be more complex for the directionally boundary conditions. Okay, and we also like higher AC schemes. Okay, so both of them are into consideration. And secondly, we also introduced to design high-order AC scheme for this nonlocal in-time models. This model is a novel model proposed in this paper. Okay, so it's just a one-sided nonlocal gradient operator to denote the time operator. In this paper, we only show the well-posted news of this model and just one first order AC scheme, so it's necessary to design high order discretization for this non-intact model. We also try to seek more application for this non-local phase field crystal model, such as the crystal lattice structure and some green boundary growth. Okay, and there are some challenging but promising projects. Okay, so first, we are interested to consider inverse problem on the parameter identification and recovering kernel in non-local operators. So far, we have efficient solvers for forward problems. So hopefully, we can get some inspiration from brand deconvolution for the kernel recovery. Okay, and we also try to make use of the sharp interface in the nonlocal Allen-Cahn equation. Actually, not just nonlocal Allen-Cahn equation. It actually also appeared in nonlocal Cahn-Hilliard equation. We try to use them for such as two-phase flows or image impedance. And thank you. Okay.